I'm not going to talk, oops, that wasn't a new one. I'm not going to talk about section 1.1. It's more about data values and doing some grunt force computational things. The stuff that's in section 1 we will hit when we need it, but we won't need much of it besides doing relative frequencies, which just basically is figuring out a percentage of the data that does something. So it's a proportion, a fraction, what have you, a percentage, and we will get to that. We will use it when we get to it, but it's a concept that I'm sure you're familiar with anyway. So that's why I'm not going to spend time on section 1.1. So we're going to go right into probability properties in section 1.2. Can you see it okay with the lights on, or do I need to turn the lights off? We're good. One of the reasons why I do this is because I'm recording lecture. So don't say anything you don't want to last forever. It's going to go on the internet. You know, anything that goes on the internet lasts forever, right? What I do is I record lectures. I post them on my YouTube channel. It's the only thing on my YouTube channel. Very exciting channel. You all want to subscribe immediately. If you just search for my name, Joe Stickles will be the first one that pops up. Students have told me they like to watch them, especially A if it was class, or to review for exams and stuff. So, look out there. Use it or don't, it doesn't matter. As long as some people think it's useful, I'll do it. So, if everybody tells me that it sucks and they don't want me to do it, then I'll stop doing it. People like this. Don't bad each other. 9 subscribers. What's that? I do have 9 subscribers.
Pretty good here.
Yeah, that's great. Oh, thank you.
Stickles has like 24. He only has 2 videos.
I have a bunch of videos up there for different classes. I will also try to remember to organize these as a playlist so that you can actually just click on your class and not have to go try to find the video just buried wherever it might happen to go. I also save it by the date, so you'll know what day the day's date is for the lecture as long as I remember what the date is, which isn't necessarily a given. All right, so anyway. So one of the things that we'll notice in the first couple of sections in this chapter is that there's a lot of overlap between the beginning parts of probability and what you've learned in discrete math if you've had the discrete math class. If you haven't, that's okay. When you take it, you'll see a lot of overlap between those two classes. So there's a lot of overlap between set theory, and there's a lot of overlap with counting methods. And we're going to go over them, what we need for this class. So it's not like you have to, if you haven't had discrete, it's okay. We're going to learn what we need to know. But there's a lot of overlap between those things. So if this stuff looks familiar, that's a good thing. Right? Building on other things. As we go along, we're going to do a lot of the stuff that has the discrete math idea, because we're going to do what are called discrete probability distributions. Probably the most famous isn't the word I want to use. Probably the easiest one you know is just the distribution that talks about heads or tails, flipping your coin, right? That's an example of a discrete probability distribution. You've got 2 possibilities. Either it's heads or it's tails, right? And if you really want to start assigning mathy things to it, you could say heads has a value of 0, tails has a value of 1. Okay, you know, there's a 1/2 chance that you'll flip either. So that's an example of a discrete probability distribution. The reason why is because you can get heads or you can get tails. You can't land on the edge of the coin. Or have the coin almost land above us. Have it land like 66% heads. Okay? And either it's heads or it's tails, right? So that's a discrete idea. There's not a whole continuum of values that you can get. Later on, we'll talk about continuous distributions. And then we'll start using some calculus on some ideas. Mainly integration and differentiation. Those are the 2 big things that we'll be using. Mainly the integration part, but some differentiation as well. So, anyway. The whole point of all of that was you're going to see some overlap with what we're doing here and stuff that you've already seen in other classes. So, just to remind ourselves, one of the things we like to do with sets is represent them with a Venn diagram. Get off the screen. All right. So a Venn diagram is just a visual representation of how sets interact with each other. So when you draw a rectangle for a Venn diagram, This usually refers to your universal set. So universal set is just your set of elements under discussion, whatever that happens to be. For our purposes in that flipping a coin idea, our universal set would be the set of possible outcomes from flipping a coin one time. So our universal set would then just be heads, tails. There's only two possibilities, right? Now, if we were to flip a coin two times, our universal set would get a little bit bigger, because if I flip two times, I can get heads, 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 tails, tails, heads, tails, tails, right? So there would be four things in the universal set. Anyway, the universal set is typically what we refer to as the set of elements under discussion. Whatever under discussion means. So I'll put quotes around that. I'm using set theory language right now. I'm going to switch this over to probability language in a minute. So the universal set is going to have a different name here in a minute. And if my handwriting is bad, so if there's something you don't understand what I'm writing, just yell at me. Okay. I'll erase it. All right. So Venn diagram, the big rectangle is your set of elements under discussion. All right. So when we flip the coin one time, we know that there's two possible outcomes, heads or tails. In general, if I've got a set of possible outcomes, I'm going to be interested in a piece of those things if I want to know the probability that something happened. Right? For example, let's do a little bit more interesting example. I roll a six-sided die one time. My possibilities then are the numbers 1, 2, 3, 4, 5, 6, right? So in that case, my universal set, or my set of objects under discussion, would be the numbers 1, 2, 3, 4, 5, 6, right? But I want to know a probability of, say, rolling an even number. Well, in that case, I've got three possibilities at work, right? I can roll a 2, or roll a 4, or roll a 6. So that's a piece of the universal set, or a subset of the universal set. Hopefully some of these words sound familiar, right? Subsets of the bigger set. So we're looking at subsets, and in Venn diagrams, we represent those typically with circles. So I'll just call that one A for lack of a better letter. Usually we will denote sets by capital letters, just by convention. Sometimes we'll just write out the name of whatever the set is, but a lot of times we'll use a capital letter to denote a set. So all this A means here is it's just some subset of the universal set. That's all it means. If I have some other set B, that's going to be a subset of the universal set, well, there's plenty of places I could draw it, right? Say maybe I draw it over here. If I drew my A and my B, where there's no overlap at all, how many elements do you think A and B would have in common? None, right? Okay. So in this case, A and B have no elements in common. These two sets would be referred to as mutually exclusive. The way I've got this drawn, so just write that down. If A and B have no elements in common, well, actually, I used the wrong words. I did use probability words. I want to use set theory words to start with. Then A and B are called disjoint. I'm trying to mirror the set theory language with the probability language, and I use the probability language too soon. Disjoint. If A and B have no elements in common, they're disjoint. So this would be a Venn diagram that represents exactly that. We've got two sets, A and B. They have no overlap. So this would be the drawing of disjoint sets A and B in some universal set U. Okay? That makes sense? This stuff sound familiar? Let's want to make sure that we're all on the same page. Yeah. Because the underpinnings of the stuff that we're going to talk about with probability theory all are based in set theory. So I just want to make sure we're all on the same page and all use the same words. All right. What if I drew my Venn diagram this way? What relationship would A and B have in this case?
A is a subset of B, which is a subset of U.
Good, good. Good. So they're both subsets of U because they're both going to be in our universal set. That's good. And then I've drawn my set A completely inside my set B. So since the set A is completely inside the set B, we say that A is a subset of B. And the definition for that is if subset, we'll label it subset of B if every element of A is also an element of B. The notation here is supposed to remind you of a less than or equal to sign. We use a little, looks like an elongated C, and then a little bar underneath it. Again, it's supposed to remind you of less than or equal to the elongated C for containment, if you will. So this is the notation for a subset, and we will use this notation, well, I will say off and on throughout the semester. All right, so we've kind of had the two extreme cases that I just drew Venn diagrams for. We had the case where they had no overlap at all. We had the case where one of them was completely inside the other. Ordinarily, if I pick kind of two sets of objects, we don't expect either of those two extreme cases to happen, right? If I reach my hand in and grab a thing of Fruit Loops, and I reach my other hand in and grab a thing of Fruit Loops, I'm going to expect some red Fruit Loops fall in both hands. Right? Okay? I expect it, but I don't expect to have the exact same thing in both hands. I expect to have some overlap, some in one that's not the other, and vice versa. Right? So usually when we draw a general situation for a Venn diagram, we'll draw overlapping circles. And I'm going to stop putting the little U on the outside just because it's superfluous. We know it's the universal set. All right, so this part in the middle, this overlap, we refer to as the intersection. If I can spell. So the intersection is what A and B have in common. It's the and. All right? So the notation is a little upside down U. Going back up to the notion of disjoint, when we had the two circles that had no overlap, so this picture, what would I say about the intersection of A and B? Yeah, it's the null set. It's the empty set, right? They have nothing in common, correct? So in this disjoint, for this disjoint part, we would say that the A intersect B is empty, and then we use a little, it's supposed to be a Danish 0, Danish O, Danish O, I mean, for the empty set, the null set. All right. A couple more ideas here. So the overlap is the intersection. The other one that we talk about with the two sets together is what's referred to as the union. Let me just draw a different picture here. I shaded everything in. The shading part here is the union of A and B. when we take that frown and turn it upside down from the intersection to the union,
Sorry, I feel bad.
I know I have really bad jokes. You still laughed, didn't you?
As long as I make it into the YouTube video, I think we're all happy.
I think we're all happy. That's right. It's in the YouTube video, exactly. All right. So the important thing to remember about union, intersection is pretty self-explanatory. It's the stuff that's in both of them at the same time. Union is one or the other, but it can also be in the intersection too. Is one or the other or both. Sometimes when people hear the word or, they think one or the other, but not both. Right? Either or. But for union, it's important to know that it can also be in both at the same time. Okay? All right. One more concept with Venn diagram, and then we'll switch over to some probability language here. And I'll just draw one picture. Here's my set A, and I'm going to shade outside. So I'm looking at the things that are not in A. So that is the complement of A. With an E, not an I, you're not telling it nice things. Oh, you're looking very well today. I told you, bad jokes. The complement of A is a set of elements in the universal set that aren't in A. Oh, and depending on what book you use, there are at least 3 different notations for complement. At least. This book uses what I'll call the prime notation for complement. This book uses A prime. You might also see A bar. You might also see A to a superscripted C. The reasons why I'm telling you this. One, if you go and search out other sources for review purposes, whatever that happens to be, whether you're reviewing for exam P, whether you're reviewing for the math certification exam, content exam, or an accreditation exam for engineering, whatever exam that you might be studying for, or whatever purpose you might have for reviewing, you might see a different source with a different notation for complement. Okay? Yeah. I will use prime. It's quicker to write.
Tell them about the U minus A and U over A too, because I've seen those a lot of higher math books.
For set difference?
For complement.
Oh, yeah. Yeah, we'll talk about set difference for a second. Yeah, you're right. Yep. All right. Are we okay with these, though? Okay. All right, so what Sam was mentioning was the idea of a set difference. So I'll draw that with a picture, too. Like pictures? There's a picture. That's everything that's in A that's not in B, right? There's a couple of ways to write this, but set difference would be A minus B, or it looks like this. These two things are set difference. This means everything in A and not B. Which what Sam was mentioning was that you can write complement the same way. If I use my universal set in the spot for A and A in the spot where B is, you can also use those two things for complement of A as well. Luckily, we won't do a lot with with set difference. It's possible, but we won't do a lot. We'll usually formulate things that we can with intersections and complements instead. Because I can also write this as A intersected with the complement of B. It gets the same answer, right? if I do A, which would be the whole circle, and it intersect with everything outside of B, I get that piece exactly. So I can also do it that way. And that's how we'll formulate most things without having to get into set difference. All right, how do we change this over to probability? Well, for probability, the first thing we need to do is we need to have an experiment. And usually experiment, at least if you've taken science classes, experiment kind of is a word that evokes a very specific thing, right? You take some chemicals and you dump them together and see what happens. That's an experiment, right? Or you take a ball and you throw it up against the wall and see where it ends up, right? Whatever, I don't know. I did put along as taking physics or chemistry. So, pouring stuff together and just seeing what would happen, see what would happen. Probably had runs and errors of like 1,800% in my lab, high school chemistry, but yeah, I'm not a chemist, so that's okay. Anyway, but for mathematicians, an experiment is a very general thing. It's pretty much anything that you can do where you can record the outcome. That's all I mean. So flipping a coin is an experiment. Rolling a die is an experiment. Right? Taking items off an assembly line and testing them for whether or not they're defective is an experiment. Right? Taking a car and crash testing it and recording the results is an experiment. Anything that can be done and results collected is an experiment. That's all we mean. Okay? So just to write that down, this is anything that can be done and exact results collected. That's all we mean. Which means for our introductory purposes, they become very contrived, but in real life, you've got very, very specific things you might want to do. Pardon me. There's a reason why stores have gone to those shopping carts. Kroger has a shopping cart. Make a little more sense of it. Actually, still Kroger here. But Kroger has a shopping cart where you go in, you scan it, and they give you deals or whatever. They're collecting data on you because they're trying to figure out how can I pick out coupons to send you to get you back to come in and buy more stuff. So based on what you bought, that's the experiment. They're running a probability of the items that you will buy to offer you enticements to come back in. That's an experiment for them. Okay? Weird experiment. Okay? Not very cloak and dagger, but that's an experiment. It's very devious, isn't it? Seeing all these old movies with all these, things bubbling in the background, collecting data from shopping, Ooh, I bought 3 apples today. Right. Anyway, that's what we mean by an experiment. So the results of this experiment, the set of possible results of an experiment is referred to as the sample space. So this is where I was talking about. I want to tie together the language of set theory and the language of probability. Remember the universal set was a set of all items under discussion? That's what the sample space is for probability. The sample space is your universal set. Right? We phrased everything above in terms of subsets of the universal set. Well, in probability, we refer to those subsets as events. An event is a subset of the sample space. All right, so, okay, now we've got some of the language down. we'll get some more of this language down. We're still going to use union and set intersection. Those actually don't change words. But when we talk about probability, we think about chances something happens, right? We talk about flipping the coin. Half the time it comes up heads, half the time it comes up tails. So we've assigned a function, if you will. I input heads, I get out a half. I input tails, I get out a half, right? When I take all of those possibilities, I should add up to 1. I should add up to 100%, right? So when we talk about probabilities, it's actually a function that we make on the set of subsets of the sample space. So let's write this down. The probability of an event, and I'll give the event a name A, is a number. We're going to refer to this in function notation to start with, P of A, where P is a function from, where does the function come from? Well, let's think about it. Events, we want to plug in an event and get out a number. Okay, so we refer to it as a set function. We're putting in sets as your inputs and getting out numbers as your outputs. Right? So the inputs are all subsets of the sample space. If we take the set of all possible subsets of the sample space, that's referred to as the power set of the set, right? Remember that from discrete. The set of all possible subsets is the power set. Not as worried about that, okay? But that's a word that you'll see in discrete if you haven't seen it before. So I'm going to write that down as part of the definition. It's from the power set of S. I'm using S for sample space here. That's pretty common. Like we used U for universal set, I'm using S for sample space. Okay, as a function from the power set of S, again, power set just means set of all possible subsets. Okay. All this means is what we're going to be plugging into this function is the events. Okay? The events are subsets of S. Okay? That's all it means. 2, well, what can I assign this to? Well, I want this to be a probability. Does it make sense for a probability to be negative? I mean, people make the statement, there's a less than 0 chance of this happening. But that doesn't really make any sense, right? The lowest probability you can have is 0, right? And for probability higher than the extreme, the highest probability you can possibly get is 100% or 1, right? As many times as someone tells you to give 110%, right? The probability you can only get up to 100% for 1. So it goes from the power set of S to the interval 0, 1. Now, not any old function will do. Okay? We have to have some certain properties that have to be met. The reason for that is I can't assign the probability of every event to be 0. 0 means it's impossible to happen. If I flip a coin, something had to happen, right? So I can't say the probability of heads and the probability of tails is 0. That constant function into the interval from 0 to 1 doesn't work. Right? Same thing, I can't assign everything to 1. Probability of 1 means it's guaranteed to happen. I can't flip a coin and say, oh, look, the probability of heads is 1. Probability of tails is also 1. It doesn't work, right? Those are heads and tails on both sides of the coin. Okay? So we need this particular function to satisfy properties. All right, so let's think about what we just said. Well, two of the properties that have to be satisfied are 2 that I just said. One of them is what I just said, and the other one actually makes sense for the rest of it. First property, I cannot have any negative probabilities, so that makes sense. And notice I already said it was from 0 to 1, so that one, this is just a list in the book. I made this by default by saying that my range of the function had to be from 0 to 1, right? Now, I do want something to be guaranteed to happen. I said that it's not possible to say it's guaranteed that heads happens and it's guaranteed that tails happens. But if I would switch the and to or, I am guaranteed that heads happens or tails happens, right? So there's a particular subset that I want to be able to plug into this function and get 1 out. Well, no matter what I do with an experiment, the outcome has to be in which set? The universal set, or the sample space, right? So if I take the probability of the sample space, that has to be 1. Okay. All that's saying is that all that's saying is that if you run an experiment, the outcome has to be in your sample space. All that's saying. Which makes sense, right? If I run an experiment, it has to be one of the possible outcomes. All right, so what is the other possibility here? Well, we need to have a way of doing kind of some compound event ideas. And those compound event ideas are if you run into a union. Now, usually when you think about unioning things together, it's putting one set and tacking another one on it, and it adds them together, right? If you count those things up, though, if you've done some counting problems with unions, you know that there's some issues if they intersect, right? To count things up, because if you count everything that's in A and count everything in B, you've counted the stuff that overlaps twice, right? So the third thing that has to happen is that if I've got the probability of a union, and this could be a finite or infinite union. That's why I put ... here. So you might want to just note that this ... could stop or it could keep going. Okay. This will equal the probability of the individual pieces if these sets are pairwise disjoint. So this third piece is important to be able to do the probability of a union. I can split up a probability of a union as addition of the probabilities as long as there's no overlap. And we will use that in solving some problems later on, probably on Wednesday. But let's see if we can use this idea of this set function for probabilities to prove a few results. Okay, so first one, fairly straightforward one. If I have an event, either that event happens or it doesn't, right? What I mean by that is either the event occurred or the complement of the event occurred, right? For example, if I roll a die, either I rolled a 1 or I didn't roll a 1, right? What's the probability that you roll a 1? 6. The probability you don't roll a 1? 5, 6, right? If I add those two things together, what do I get? 1, right? 6, 6, and 1, right? And think about what I did. Either I rolled a 1 or I didn't roll a 1. That's the entire sample space, isn't it? So one of our first theorems that we can prove by the way, when I write theorem, I'm lazy and I just write thum because I'm lazy. Mathematicians are inherently lazy. Look at all the symbols we use. Okay? All right. So, for any event, the probability of A plus the probability of its complement has to be 1. The proof of this, or the poof of this, because I also abbreviate proof, the proof of this is fairly straightforward. You just told me that if I take A and combine it with its complement, what do I get? If I take A and union with its complement, what do I get? The universal set of the sample space, right? So I get the whole thing. And what do I know about the overlap between A and its complement? It's empty, right? I can't be in A and not be in A at the same time. Do we agree? Okay. So since those two things are true, we have, I know that the probability of A union A complement must be the probability of S. That's just applying the function to both sides, right? This is a little bit of a review. Functions, if I plug one thing in, how many things are going to get out? One, right? If I plug a thing into a function, I get a thing out, right? Not 7, right? So if this is equal to this, then their outputs have to be equal. I can't get two different things out, right? The right-hand side is equal to what? Probability of the sample space, what's that equal to? It's 1, right? That's one of our properties of being a set function, correct? Like a probability function, right? This is 1. How can I rewrite the left-hand side? This is equal to 1 by property 2, right? That one that's up there. What can I do with the right-hand side? Or the left-hand side, sorry. Well, I want to use one of the other properties. I can distribute it as a plus sign, right? Okay. So I can make this probability of A plus probability of A complement. Again, this part from here to here uses property 2. From here to here uses property 3. Notice I stated the hypotheses that I needed for both of those, right? I needed that their union was equal to S, so I could use property 2 for the right-hand side. I needed them being disjoint to get the left-hand side, to use property 3. Now, or if this is a straightforward proof of this statement, now usually we'll see this statement written as solving it for probability of A complement. Usually you will see this written as probability of A complement is 1 minus the probability of A. That's ordinarily how you see that written. And we will use that property to solve some problems later on. Any questions on that one at all? Well, actually, let's go ahead and use this property for the next theorem. I'm just kind of following along in the book where we've got these theorems. Notice that the probability function doesn't say anything about doing the empty set, but it does say that the probability function takes any event, any subset of the sample space. Going over set theory, the empty set is a subset of every single set. So we should be able to calculate the probability of the empty set. Now if I run an experiment and record the result, something had to have happened, right? So what should the probability of the empty set be? 0, yeah. So the theorem is that the probability is 0. How do we prove it? Well, let's think about using the previous result, because that's one thing we do in mathematics. I like to call it the 11th commandment. Thou shalt use the theorem that was in the section that followed, so I solve all problems following that section. Right? The only thing we have is the previous result, right? The previous result talked about probabilities of complements. What set is the empty set a complement of? The sample space, the whole thing, right? The empty set is the complement of the entire sample space. So since the empty set is the complement of the sample space, we have the probability of the empty set is the probability of the complement, but by the previous result, how do we calculate probabilities of complements? 1 minus the probability of the set, right, the event. And what is the probability of the sample space? 1. Hey, look at that. We proved that it was 0. This is as good a place as any to stop, and we'll do some more of this in a second. But this is something that I want to point out. Notice that we had some things that the probability function had to satisfy. We could have also put in that definition the probability of the empty set had to be 0. It wouldn't have changed anything because it's true. But that's really bad mathematics. You don't want to assume something is true that you can prove is true. It makes your mathematics weaker to assume things that you can actually prove. In particular, it introduces ways to start throwing contradictions into your axiomatic system. If you start assuming things that you don't know for a fact are true or false or unprovable, you can run into issues. So one of the big things that set theory people worry about is, are statements provable given the axiomatic system that you have, or are they what's called independent? We're not going to do a lot with that here, but I just wanted to mention why we bothered proving it, but we could have just said it. Especially for something that should have been obvious, right? That's why we prove it, though. Right? It's bad mathematics to assume things that are true that you can actually prove are true. That's what we did. That's why I thought it was a good place to stop. At the end on that. All right, we'll see you Wednesday. Don't worry about we're doing problems. I'll give you an assignment on Wednesday to do.